Namaste, Namaste everyone. Welcome to Ray Optics class. We have seen the refraction through many surfaces, curved as well as plane surface, prism, and different image formation in the case of convex lens, concave lens, and problems related to lens maker's formula, curved surface refraction and all. Now we are in the last part of this chapter, that is how do we construct microscopes and telescopes. Already we have seen one small microscope, that is simple microscope. That job will be done by this convex lens. When the object is within the focus of the convex lens, we get enlarged virtual image, and that is called simple microscope. So shall we draw, suppose you are asked to draw the ray diagram for simple microscope, you have to draw that condition where virtual enlarged erect image is formed by a convex lens when the object is within the focus. So let us take a convex lens of certain focal length, and yes, f and f, and here is also focus, okay, 2f, and this is f, and this is 2f. Now place an object within the focus like this. When we place an object within the focus, we have to consider two rays of light. One ray parallel to the principal axis. Better you draw this. You take a pen and paper, draw along with me. If you don't draw this diagram, you will never draw it in the examination. You have to draw it. So take a pen and paper, be ready with that, and you are drawing a simple microscope now. Simple microscope is that convex lens which forms virtual enlarged erect image when the object is within the focus. So you have to consider two rays of light. One coming from, both coming from A, one ray passes through the focus like this. A ray of light incident along the principal, parallel to the principal axis after refraction passes through focus. And another ray of light passing through the optic center like this. O, the midpoint of the lens, surface of the lens. And it passes like this, and both these rays never meet. They never meet. They diverge. So, this is focus, yes, they diverge. If a person looks into these two rays, and if he receives these two rays, he feels that these two rays are coming from some point here. Okay, I'll rub this. These rays appear to diverge from this point somewhere here, and this point acts like an object, and this is the virtual erect image formed on the same side as the object. So if I call this as B dash, this is A dash, okay. So one ray parallel to the principal axis passes through the focus, another ray passing through the optic center moves undeviated since the lens is very thin. These two rays diverge, they never meet, they appear to come from a point here. So this point acts like a virtual erect image of this point. So totally the image will be formed here. So A dash B dash is the virtual enlarged image. So you have to adjust the lens in such a way that you will get an enlarged image. Okay, so this is a simple microscope. So there are two types of microscopes that we deal with. One is simple microscope and another is compound microscope. Okay, right. Now, how much enlarged image is formed? Okay, this is one way of getting an enlarged image. Now, if you want still enlarged image, what you have to do is you have to bring the object closer and closer to the focus. Suppose the object itself is at focus. What is the how will be the image? Suppose you are very close to the focus. This is focus, this is another focus here. If the object is very, very close to the focus or on the focus, what happens? A ray parallel to the principal axis after refraction passes through the focus. Another ray of light passing through the optic center and becomes parallel, almost parallel, right? So like this. Now, if these two rays are produced backwards like this and like this, they never meet. They never meet here, and they don't meet back if they are produced backwards also. Suppose this object is little bit within the focus, these rays will diverge in such a way that they appear to meet at a very large distance backside. They appear to come from a point which is very far away. Now you get very, very enlarged image. Now we say that the image is formed at infinity. This is also moving up to infinity. These two rays move to infinity. So we say that the image is formed at infinity. Infinity in the sense, compared to the size of the lens, the image is very large and it is formed far away. So this is also a microscope. Very enlarged image is formed, very large enlarged image. So here a limited enlarged image is formed. Now whenever you look into an object, or if you are looking into some sentences using this lens, convex lens, you will adjust the lens in such a way that you get the enlarged image. If it is a reading lens, you will adjust the lens. But because here, for example, if you want to see what is written on the board, and if you want to see the enlarged image, you will take the lens and adjust it. Because why do you adjust it? You can't bring the board closer to your lens. Bringing the lens closer to the object and far away is easier. So when you bring it closer and far away, you adjust it till the object comes within the focus. How much within the focus? Till the image is seen clearly in your eyes. And every eye has a factor called near point, yes, near point, or least distance of distinct vision. Least distance of distinct vision. Near point or least distance of distinct vision. What do you mean by least distance of distinct vision? You might have studied this in your lower classes. Of course, you must know this before going to this. This is not a part of syllabus. And remember, in that syllabus, even if you have in the textbook the things like rainbow formation and refraction of the atmosphere and eye, defects of eye, all these things are deleted now. You don't have that in the theory part. So you can leave them. Eye defect, myopia, hypermetropia and their corrections, these are all deleted because they are already studied in the lower classes for that reason. And this least distance of distinct vision, far point, near point, everything. Formation of rainbow, all these things are very basic, so that's why it is, even though it is in the textbook, you need not read it. But if you read it, it is better, you must know it. Okay, what do you mean by least distance of distinct vision and what is the near point? Both are same. When you bring an object very close to your eyes, eye lens has the ability of adjusting itself for the formation of an image. The structure of eye is such that, suppose this is optic nerves which are going to brain, and here are ciliary muscles, right? And these in between the ciliary muscles we have eye lens. And of course, now eye lens will be having, it will change its radius of curvature, both the surfaces, by bulging itself when it is compressed and becoming very lean when it is expanded. So these ciliary muscles will contract and make the lens very bulged like this. And these ciliary muscles will expand and the lens becomes very thin. And you know that the focal length of any lens depends on the radius of curvatures of the surfaces. So when it becomes thin, the focal length will be different. When it becomes thick like this or bulged, focal length will be different. Because here you have already fixed retina, screen. Screen is already fixed. You can't change the position of the screen. Lens is already fixed. So image distance is fixed. You can't change the image distance as you want. Then where is the object? Object distance is not fixed. Object distance keeps on changing. You may be looking into a very close tree or a very far away hill or stars, moon, very very far away distant objects also. Very close distant, very closely spaced objects also. All the objects when they are seen from the eye lens, image should be formed on the retina only. So who will adjust now? Lens itself has to adjust its focal length so that image is always on the retina. And now eye lens, as you bring an object closer and closer, eye lens will be bulging and bulging. Its radius of curvature will decrease, it will bulge, and when it bulges, the image will be formed on the retina, and there is a minimum, or there is a limit up to which this lens can bulge, and ciliary muscles can apply pressure on the eye lens, and beyond that ciliary muscles cannot contract. What do you mean by that? As the object is very very far away, suppose you are looking into a very distant hill, your eyes are fully relaxed. So if you want to relax your eyes, you have to look into a very far away object. The ciliary muscles are in their relaxed position and eye lens is very thin, image is easily formed on the retina. Bring the object closer and closer and closer. The ciliary muscles get contracting, keep on contracting, eye lens will be bulged and bulged and bulged, and image is always formed on the retina. For every position of the object, eye lens will adjust itself so that image is formed on the retina. But there is a limit for the ciliary muscles to contract. Beyond that they won't contract. Beyond that the eye lens will not bulge. That means if you bring the object beyond certain limit, clear image is not formed on the retina, because eye lens cannot adjust beyond that. Ciliary muscles cannot contract beyond that. At that moment what happens? Contraction stops, and if you bring the object further closer, the image is not clearly formed on the retina. So if you bring a chalk piece or your finger, there is a limit at which a clear image is formed. What is the minimum distance at which an object can be clearly viewed? So if you keep an object here, say ciliary muscles can contract and image is formed on the retina, say. If you bring it beyond, within this, say no image is formed. Then this distance is called least distance of distinct vision, D, and for a normal human being it is almost 25 centimeters. Small, around 25 centimeters. So what do you mean by near point is 25 centimeters? What do you mean by least distance of distinct vision is 25 centimeters? An object kept at 25 centimeters can be seen clearly. An object kept beyond 25 centimeters can be seen clearly, but an object kept within 25 centimeters cannot be seen clearly. The minimum distance between the eye and the object at which the object can be seen clearly is called least distance of distinct vision. Now coming back to this simple microscope. If you want to see this diagram, you will hold the simple microscope, that is convex lens, like this. If you want to see the clear image, you will adjust this. So why do you adjust this? Because object must come within the focus. How much within the focus? That's what we were discussing. How much this object should come within the focus? Suppose this is the lens handle, you will hold the handle and you will move the lens in such a way that object comes within the focus. And you will hold it within the focus, or you will hold the lens such that the object comes within the focus till this image is formed on least distance of distinct vision. Because you can clearly see this now. If the image is formed within the least distance of distinct vision, you can't see that clearly. Suppose, sir, object is exactly at focus, image is highly enlarged and formed at a very large distance. Of course, this is a relaxed position. You can see the image in a relaxed mood. But still, if you want to get a clear image, this is another possibility when the object is within the least distance of at the least distance of distinct vision. This is the nearest distance at which image is formed. Suppose you bring the object still closer, won't you get an image here? Yes, that is also possible, but that image cannot be seen clearly by the eye. So we adjust the lens such that image is suitable for our eye, so that the distance from the lens to the image is least distance of distinct vision. So can I treat this as the distance at which I can see the image clearly, capital D? And if it is so, I'll rub this now. For this one, what is the magnification? How much is the magnification? How much magnified image from the object is produced? Magnification. Magnification is, you know that magnification is V by U, right? And also you know that, now I will try to substitute for 1 by U. 1 by F is equal to 1 by V minus 1 by U. You know this formula. And shall I substitute for 1 by U? I will bring 1 by U here, it becomes positive. 1 by F here, what I will interchange the positions. 1 by U here, 1 by F here. 1 by U is equal to 1 by V minus 1 by F. M is equal to V into 1 by U. 1 by U is 1 by V minus 1 by F. Right? Now, you bring the V inside. V into 1 by U. 1 by U is 1 by V minus 1 by F. Substitute here. Magnification is equal to V into V, or V by 1 by V. That is equal to 1 V by V minus V by F. Now what is V? V is image distance. Where is the image now? We have adjusted the lens in such a way that image is formed at least on the least distance of distinct vision, where you can see the image clearly and enlarged. and if V is D, D is in the left hand side. It is in a position which is opposite to the incident rays of light. Incident rays of light are here like this. So I should substitute minus D. Image distance V is equal to minus D, because image is at the position of least distance of distinct vision or near point. So how can I write the magnification formula? M is equal to 1 minus D by F, right? Minus D by F, one minus from the formula, another one minus D. So what is the final answer for magnification? M is equal to 1 plus D by F. This is the magnification formula. So in the examination point of view, you may be asked only with the 2 questions. Draw the diagram of a simple microscope. This one. How many lenses will it use? Only one. And what type of image is formed in a simple microscope? Virtual, enlarged, erect. Right? Microscope is an instrument used to show the enlarged image of the object, and it is erect also here. And what is the formula for magnification of a simple microscope? Magnification M is equal to 1 plus D by F. What is D? Least distance of distinct vision. The minimum distance at which the object can be seen clearly, and our image can be seen clearly. F is the focal length of the lens. So that is the thing for simple microscope. Now we will go for compound microscope. What do you mean by compound microscope? Compound microscope uses 2 lenses. So I'll rub this. I'll write the magnification formula here. M is equal to 1 plus D by F. This is M. We will go for compound microscope. What is compound microscope? Now what I'll do is here, I will have to have an object within the focus, right? But before having an object, let me produce an enlarged image of an object and let that image come here. Let me magnify this object's image once and I will keep it here. It will be like this. You take a small lens first, right? And you know that convex lens produces real enlarged image. When will a convex lens form real enlarged image? It is when the object is between focus and 2f, f and 2f, because you know that anything beyond 2f in a lens, anything beyond center of curvature in a mirror are larger, whether it is image or object. Anything between f and c in a mirror or f and 2f in a lens should be diminished. Now I will keep an object here, small object. It will be produced, its image will be enlarged and it will be formed beyond 2f. So what I will do is, I will take one ray of light, let it pass through the focus, and another ray of light passing through the optic center. It passes undeviated. So did I get an enlarged image? So the small object's magnified image is formed here. I will discuss the rays of light first, right, in all microscopes and telescopes. Then we will go for the magnification. So the enlarged image of the first object is formed here. Now why can't you treat it as an object again? This can be treated as an object. How? Take another lens. Let this image produced by this lens serve as an object here within the focus of this one. So this is the lens which forms the final image. So let me keep another lens here, right, like this. Let me keep another lens here, and this is called objective. What do you mean by objective? Objective is a lens in front of which object is kept. Objective is a lens which receives rays of light from the objective. I call this as eyepiece. What is eyepiece? Eyepiece is a lens finally through which we see and image is seen. Eyepiece is the lens through which we see. Finally refracted rays go out. And object is the lens which is kept in front of the object and it receives the incident rays. Okay, so these rays form an enlarged image here. Okay, right. Now these rays enter here. Now you have to adjust this lens in such a way that this image which serves as an object for this should lie within the focus of this one. So shall I call this as focus of objective, double the focus of objective, and this is focus of eyepiece. This one is focus of eyepiece, right? This one is focus of eyepiece, eyepiece, because we have two lenses. So you have to adjust this lens in such a way that this image lies within the focus of this lens, that is this one. I have indicated the focus here, FE. So this should be a point. Don't mistake it like an arrow mark. So this is the focus of eyepiece here, this one. Okay, sir, how to adjust it? Suppose I keep a lens in such a way that I will keep a lens. Suppose this image is somewhere else. Won't I get the image? No, you won't get the image. So how to bring this lens then such that this image is within the focus? Only the thing you have to do is, if you want to bring this within the focus, arrangement will be given. Both the lens will be kept in a tube like this. One tube flows over another tube. So there will be two tubes. One tube moves over another tube like this. Rack and pinion arrangement. Usually you have it in a telescope and microscope. You can move the two tubes like this. When they move, and you will be given one screw here. When you turn the screw, this one tube moves over another tube, and here is the objective, here is eyepiece. Suppose the image found by the objective doesn't lie. So here is objective, image formed by the objective doesn't lie within the focus of eyepiece. You move this tube, rotate this so that this lens comes forward and this image lies within the focus of this eyepiece. You can do that. So you can adjust the positions of the lenses using rack and pinion arrangement, in which two lenses are kept inside two tubes which move one inside the other. So the distance between the lenses can be adjusted. But now this should lie within the focus. And you know that whenever an object is kept within the focus, it forms the enlarged virtual image on the same side as an object. Now this is the object for this lens, and these two lenses will diverge. They will diverge like this, such that image is formed on the same side and it is virtual and enlarged. So this one is like this and this one is like this. They will diverge, and if you produce them backwards, these rays appear to come from somewhat this point here, and this is the position of the final image, which is enlarged, and it is like this. So it is inverted because this is inverted. So it is in the same position. So this is the final enlarged image. And here is the position where you see the object like this. So this is the diagram of microscope, and the derivation part of that we will see that in the next class. For the time being, we will study only the ray diagram. So theoretically, one by one you have to draw. You shouldn't jump into the diagram. Somewhere from here, if you are starting and continuing like this, is not good. So first you have to write an objective, keep an object within f and 2f, let it form a real image beyond 2f, and after that serve it as an object for the eyepiece. You hold the eyepiece in such a way that this object lies within the focus of it, and then the two rays diverge and appear to come from a point here. Okay, it should be diverging according to this ray. So this should be continued actually like this, and okay, final image is formed here. This is final enlarged image. Okay, now we call this distance as something like L, and later in the derivation we can see that magnification derivation. Usually in the examination you will be asked to write the formula and the diagram. Okay, so this is a compound microscope. So how many lenses a compound microscope uses? It uses two lenses. One is the eyepiece and another is objective. But a simple microscope uses only one lens. Now we will complete the ray diagram part. That is better, I think. So what is a telescope? Telescope is a device used to view the distant objects, image of the distant objects. Whatever the telescope shows, the image is far better than the image as we see through our naked eyes. For example, telescope also magnifies the image. Here the magnification is very high. You see what is the size of the object. See the size of the image, very large. Magnification is high. What do you mean by magnification in a telescope? telescope in the image is not larger than the object. When you see through the telescope, whatever the image of the moon you can see, that is far larger than the image of the moon when you see the moon through your naked eye. When you look into the moon from your bare eyes, how much sized image is formed? When you look through the telescope, you will get a better image. That's what you call magnification. So still the image is far away. You don't see an image. When you look through the telescope to the moon, you don't see that the moon is very close and very enlarged. Not like that. It is a better image. So telescope is an instrument used to see the very far away objects. They should be seen clearly. So what are all the things, ups and downs and the hills and craters you can't see in the moon through the naked eye, can be seen when you look through the telescope. So telescope should also have two lenses, eyepiece and objective. So telescope consists of two lenses. One is objective and another is eyepiece. We will draw the eyepiece later. Okay? First we will draw objective. Now, since you are looking into a very, very far away object, what type of rays are coming from the very far away object compared to the size of the lens in the telescope? It is almost parallel. When the object is at a very large distance, the rays coming will be almost parallel. I will take 3 rays of light, or you can take even 2 rays of light, right? Either 2 or 3. So let the parallel rays of light be incident on the objective. So this is objective. Now if parallel rays are incident on a lens, you know what happens to them? They come to focus. So this is the focus, where they get focused. The arrow mark for each ray is important. Now, shall I call this distance as the focal length of objective? Yes, it is the focal length of the objective. Now you have to take another lens. Which one? Eyepiece. So I will place the eyepiece here. Shall I place the eyepiece here? This is eyepiece. Okay. How should I place the eyepiece? I should place the eyepiece in such a way that this point itself serves as the focus of eyepiece also. This is the focus of eyepiece as well as focus of objective. So focal length of eyepiece. Now you know that if parallel rays are incident on a lens, after refraction they pass through focus like this. This is one diagram. Suppose if you keep an object at a focus, say a bulb, how do they emerge out? They become parallel. It is the principle of reversibility. Light follows the same path if it is put in the opposite direction. So if parallel rays are put on a lens, they meet at focus. And if you keep an object at focus, they become parallel. That is the fate of this lens. All the rays get focused and they start from the focus, diverge, continue the journey like this. So I have to increase the size of this lens. Okay, they continue the journey like this, this one like this one like this here, and now what should they become? They should become parallel like this, right? They become parallel. So these rays originating from the focus of the eyepiece, after refraction they become parallel. For a person observing from here, imagine that the person is observing from the eyepiece. That's why it is called eyepiece, the lens through which we see the image. These rays appear to come from again infinity. So they appear to come from infinity like this, yes. Right? So I'll write F0 here, focal length of the objective. So this image formed, instead of, suppose you stand in front of the telescope and receive these rays. When you receive directly these rays, what type of image is formed in your retina? And image formed when you receive these rays, these parallel rays, will be far better now than these rays. These rays forms they do not form a better image. These rays form a better image. So this is how a telescope shows a better image of an object when it is seen through the two lenses like this. Now this distance, so here also we use a rack and pinion arrangement. How to adjust these lenses, sir? How do I come to know that image formed by the first lens exactly lies on the focus of the other lens? Just adjust it. If you don't see the image anywhere here, you just adjust the lenses in such a way that you see the image clearly. What do you mean by adjustment? You are unknowingly adjusting the two lenses using rack and pinion arrangement, again like this. So here one lens, here one lens. So this goes inside this one. Here you have a screw which can be turned and the distance between the lenses can be adjusted. Till these two lenses adjust themselves, the focus of this and focus of this lies. Then once you adjust this, what is the total distance between the two lenses after adjustment? Once you can see the clear image, then the distance between the two lenses is called tube length, and here tube length is equal to how much it is? F0 plus Fe. This is the tube length, F0 plus Fe. So that is the thing of refracting lens telescope. So this is a refracting telescope, because here both the lenses are used. They are refracting light and that is tube length. Of course, I can do one thing here. Remember all these types of image formation and keeping the lenses helps you a lot in solving entrance exam problems. Now this length is F0 plus Fe. Suppose the two lenses are very long. Of course, now I am going little away from the syllabus. Sir, I don't want such a long tubed telescope. I want a shorter one. What I can do? If the tube is very long, it is F0 plus Fe, I can reduce it. I can use a concave lens. That is called Galilean telescope. Okay. I can draw the ray diagram for it like this. That is not involved, but still you can study something from it. Now, how is that telescope? I can take parallel rays to fall on the first lens, that is objective. This is objective. Now they get focused at a point like this, and that is called focus of the objective, and this is the focal length of the objective. Right? Now these rays proceed and okay, I can do it like this. I have to take a little bit more so that the ray diagram is a little bit clear. I have to take this like this. Okay, so this is focal length of the objective. Here they will proceed like this, or let them proceed. Now you know that in a concave lens, if parallel rays are incident on a concave lens, they diverge in such a way that, like this, they appear to come from focus like this. So this becomes the focal length. Okay, F. Now suppose you keep an object, or suppose there are rays of light coming like this. Suppose the rays of light are coming like this. I'll take the reverse order, right? Now I place a convex lens in such a way that, or in such a distance that, before these rays get focused, I keep a concave lens exactly at a distance which is equal to its focal length. What will happen to these rays after they pass through the convex lens? Still they keep on converging here. A converging beam of light which appear to converge here have been disturbed by a concave lens. Concave lens is disturbing these rays. Suppose you remove the concave lens, definitely these three rays meet here. Suppose you place the concave lens, what will happen? Because they will become parallel, provided this point is exactly the focus. So you will never have these rays now, they have to be drawn by dotted lines. So if the rays which are converging towards the focus of this lens are incident, they become parallel after refraction. Of course, this ray can be shown here like this. If parallel rays are incident, they diverge in such a way that they appear to meet at focus. And if the converging rays are incident on a concave lens such that they converge at focus, they become parallel, but they can't go here. They can go and meet here only when you only when you remove the lens and make them to get focused. This is one possibility. Now we are having the problem of length of the telescope, correct? This length is very long, it's a very long telescope. I want to reduce the length. And now f0 plus Fe is the total tube length. Sir, how can I do that, sir? What I can do is, rays are getting focused here. Before they get focused here, I'll place a concave lens like this. I'll place a concave lens in such a way that this is exactly the focal length of the eyepiece. This is eyepiece now. This lens is eyepiece and this is the objective. This is eyepiece. Now what will happen to these rays? Will these rays continue to move and focus? No, they never meet and they never focus. So they don't go here. They become parallel like this. Or they will diverge a little bit more. So instead of getting focused here, they diverge because they are about to focus at the focus of this lens. So they diverge like this, become parallel. So this ray becomes like this ray will move like this. So they appear to come from infinity for a person observing from here. Now the same rays produce, instead of looking from here and getting an image, it is far better to look from here after the telescope, so that you will get a better image, and that image will be at infinity, of course, as similar to this. But what is the rack and pinion arrangement required here? Only this much. What is this distance? f0, this is total distance, this focus here, f0 minus Fe. So tube length is f0 minus Fe. This idea should be very clear for the examination, right? Entrance examination, I am saying. So if you have this knowledge, you can have a very clear problems, or very easily you can solve the problems using this idea. That's all. For that matter I have discussed, but this telescope is not included in the syllabus. You have a telescope using refracting telescope using convex lenses. But you have a reflecting telescope, cast grain telescope. What is reflecting telescope? It uses mirrors. Reflecting telescope. It uses mirrors. And we are especially using cast grain telescope. Now, what does it use? It uses, in this part, it uses a mirror. So it consists of, only ray diagram is enough, it consists of a concave mirror like this. Okay, one side. And a hole is drilled on this concave mirror. And a hole will be drilled on this. And the later part, that is eyepiece, will be kept in this tube, eyepiece here. Or shall I put it a little bit closer? Oh, here, right, like this, eyepiece. Okay. Now this is the opening, and here will be a convex mirror. And what is the use of reflecting telescope, sir? I will tell you. I will narrate you why do we use reflecting mirrors, not the lenses. What is the advantage of having this? Of course, that is also better, but there is an advantage. So just focus this or move it towards the object. Suppose a star you want to observe, or any planet or a distant object. You just focus or turn it towards that object. Parallel rays will be coming from such objects. So when the parallel rays are incident on a concave mirror, which is not complete, there is a hole inside, but you have that part of the mirror which receives light here. When parallel rays are incident on a concave mirror, they get focused, right? Say they get focused like this. Here you see convex mirror image formation. I don't keep the convex mirror now. Let they get focused here. When parallel rays are incident on a concave mirror, after reflection they meet at focus like this, right? They meet here. Now let us disturb these rays by using a convex mirror. See what the convex mirror will do. Now if there is a convex mirror like this, okay, if parallel rays are incident on a convex mirror like this, they diverge in such a way that this ray after hitting the mirror diverges in such a way that they appear to come from focus. This is F. Of course, here it should be dotted line because these rays are normally incident, come back. These rays are not normal incident and they reflect like this. And these rays, okay, they appear to come from focus at this point. Now what will be the other case? What is the other case, sir? I will take the convex mirror. I will incident two converging rays such that they are moving towards the focus like this. I will take two converging rays which appear to move towards the focus. Yes, like this. Now, if I remove the mirror, definitely they will go and meet at focus. If you don't remove the mirror, if you keep the mirror so that this is exactly the focus or focal length, sorry. If converging rays appear to converge on the focus of the convex mirror are incident, they get reflected parallelly like this, right? That is also possible. So now what I will do is here, of course I don't keep the mirror in such a way that they do become parallel. What I will do is I will keep a convex mirror in such a way that I will keep a convex mirror, and even convex mirror can produce converging rays. If I place a convex mirror like this, okay, I don't adjust this distance as focal length, they get reflected and they meet here, so that they meet here like this, right, like this, and they pass through this lens and you will get the final image. Of course, then this forms the later part is not shown here. The eyepiece here is another lens, and finally they form the image here. So this ray diagram I have to adjust little bit. So this parallel ray is reflected by the convex mirror, and this parallel ray is reflected by the same convex, of course from the concave mirror first, then from the convex mirror, they meet here, and then you get the final image, and that enlargement is done by the eyepiece. This is cast grain telescope. This is reflecting telescope because it uses concave and convex mirror. And remember, there is an advantage in the cast grain telescope, that is reflecting telescope, than refracting telescopes. One thing is, these lenses are very heavy because they are made up of glass. Mirrors are not so heavy because they are only surfaces, reflecting surfaces. They are very thin. So mounting all these things, mirrors and concave and convex mirrors in a telescope is easy because they are lighter. What about mounting the lenses? Mounting the lenses was a very heavy job. It is a very heavy job, and building a telescope is a very great work because you have to hold all those, that two tubes should hold all the heavy lenses. But here this is easy. So mounting of mirrors is easy job. That is one advantage. Another major advantage is, if you take a lens, an incident parallel beam of white light, say this is white light, what happens is, this part of the lens acts like a prism. If you take a lens will be like this, chop out one portion of the lens, it acts like a prism. So if it acts like a prism, what happens? After refraction, violet is bent more, all the violet rays get focused here. What about red rays? Red rays are bent less, so they get focused here. So the rays after refraction are multicolored, and they do not meet at the same point. Violet rays get focused at one point, red rays get focused at another point. So the image is not clear, it is blurred, and this is called chromatic aberration. You get a multicolored image, and this is called chromatic aberration. Chromatic aberration is found in lenses, that is refracting telescope. Chromatic aberration is not found in reflecting telescope. So you may be asked to write the two differences between reflecting telescope and refracting telescope. Reflecting telescopes use mirrors, and mounting mirrors is not a difficult task, they are very light. Mounting lenses is a difficult task, and reflecting mirrors do not produce chromatic aberration, that means multicolored light. But refracting telescopes use lenses where light gets refracted and dispersed. They act like prisms. and multicolored images are produced, what is called chromatic aberration, and that is not found in reflecting telescopes. So we have seen the ray diagrams. Now accept this, that in the telescope and microscopes you have to derive the equation for magnification, which I don't say that very important, but you must know it better you know it. So we will do that in the next class along with few problems. Till that, study these ray diagrams and don't leave them as it is, because if you want to draw that, you should draw it very carefully and get the answer or get the full mark. So hope you will do that. Till then, take care. Thanks for watching. Namaste.